This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, we might as well get underway again. So, thanks for coming back. We've got another exciting 3 hours almost in front of us. This is where we got up to last time when we were going through this topic of introducing compression issues, and we'd been through the entropy coding stuff, and we looked at signal structures, and we had finished looking at the basic process of transform coding, and we were up to, or just about to start this point of lossless and lossy coding. And so we'll finish that off, and then we'll look at some specific image compression examples, JPEG and then JPEG 2000. JPEG you certainly know, JPEG 2000 you might have heard of, might not be so familiar with it. All the transformations that we've looked at so far, things like predictive coding and subband coding and transform coding, rearrange the data. They transform the data, but they don't actually change the number of data points that we have to communicate. So it changes the distribution of numbers, so it gives us some potential assistance for data reduction, taking advantage of the probabilities, and it reorganises them. So the transform, the DCT for instance, pushes all the large coefficients together and the small ones are somewhere else, so it rearranges them, but they don't actually change the number of data points. However, not all of them might be needed, and or maybe they don't always all have to be represented so with great accuracy. So to decide what how accurately we need to represent these different quantities, we can go back to this very simple diagram where we were asking what the characteristics are of the source of the signal and of the receiver. And if we know something about the sensitivity of the receiver, and in the case of images that's the human eye of course, or the psychovisual system, then that will help us decide what is irrelevant and what we can throw out. So we need to take account of what the ultimate receiver of the image is. So don't worry, we're not going to look at the anatomy, it just was a graphic that filled up the slide. But we will look at the effect of, or how we can utilise the psychovisual system knowledge we have to decide what information we need to keep and how accurately we need to keep the information that we do. So if we, I presume you're very familiar with quantization, so I'll just step through this very quickly, but just as a reminder, I suppose, about what quantization is. It's essentially the mapping of a set of continuous quantities onto a discrete set. So we're effectively rounding off, where we had highly accurate information in the first set of data points. We've rounded them off to a discrete set of levels in the second. And only at this point is the coding lossy, and it's a very important point to understand. It's not complicated, but it's a very important point to understand. With everything we've done before, with all these transformations to predict some values based on earlier ones, or to perform this discrete cosine transform, within the accuracy of the numerical mathematical manipulation, we haven't changed anything. Everything is completely reversible. But only now, if we quantize, is the coding lossy, in the sense that we cannot get back to exactly what we originally started with. And more than that, if there is no quantization in the system, then it cannot be lossy. Quantization is the only point at which we lose some accuracy. So scalar quantization simply involves mapping a continuous set of values, or in the digital world, of course, we're not truly talking about analog continuous, but we're talking about a high resolution quantity on the input to a discrete set of values on the output. If we're talking of positive values, say image intensities, pixel intensities, then we have a one-sided plot like this. But in general, more generally, if we have a two-sided input and two-sided output, of course, we have a symmetrical plot. This is a uniform quantizer, of course, where each of these steps is the same size. So we have a discrete set of outputs. Any input within that range gets mapped onto the same output point. That's scalar quantization involving a single variable. We could also have which can be represented. Alternative representation is that shown at the top, where anything within the two or between the blue bars is represented by a single point indicated by the red crosses. But we could also do multi-dimensional quantization, vector quantization. And in this two-dimensional illustration, we've got two variables, two quantities that we're quantizing. It doesn't matter what they are. But as a result of analysis of the probability and the resultant distortion when they are quantized, we've decided that anything within this particular blue boundary is quantized or rounded and represented by that single red point there, two coordinates. And similarly, anything within this range is to be represented by another pair of points there. So quantization may be multidimensional. Okay. So what do we do with all these tools that we've been talking about? These transforms, the predictive coding, the removal of redundant information, and the removal of irrelevant information. By irrelevant information, I mean, perhaps the slide tells us, that which is not perceivable by the viewer or the listener. So, in other words, it's what we've just been talking about. If we quantize in a controlled way, we can remove those components that we're not sensitive to, so it involves lossy coding, but we haven't removed anything important, and so hopefully we can maintain high perceived quality. I think we've covered this. So a lossless coder is completely reversible. There are some examples. The free lossless audio coder, if any audio people are in the group, they'd be familiar with FLAC for very high quality audio that's exchanged over the internet. Apple has a lossless audio format, and there's a Meridian lossless packing format for audio on Blu-rays. I think we'll come back to that, I think. So a lossless coder can remove redundant information but not the irrelevant. Right? Why would we choose lossless? I wasn't supposed to give you the answer immediately, but you presumably realise that we would choose lossless coding when we want to maintain very high quality, either because we are audio files and have a very high quality, very expensive audio amplifier and loudspeaker system, and we believe that we need that highest quality, or perhaps we want to maintain that highest quality because we could subsequently process it, for instance doing some editing, so would maintain lossless coding in that case. When would we choose lossy coding then? Yeah, for final distribution. So when the only distortion we introduced will be acceptable in the application, and we want to save bits basically. So you can save a lot more bits once you're prepared to sacrifice some of this data. So let's move on and look at how we can bring together some of those tools we've looked at in a specific and very well known image compression system, which is JPEG. So if I gave you 5 minutes to draw a block diagram of JPEG, given what we talked about, I'm sure you would come up with exactly the blocks I'm about to show you, because it's fairly straightforward. In JPEG, we simply take the input image, we perform block segmentation, which is a fancy way of saying we split it up into little blocks of little square blocks of pixels. We perform the DCT on each of those blocks. We quantize the DCT coefficients, and we assign code words to the resultant quantized values before we send them to the decoder. And that code word assignment is simply a Huffman coder, which you are already familiar with. At the decoder, we simply do the reverse. Right? We look up our code word according to the Huffman table to obtain the quantized transform coefficients. I'll talk about this block in a moment. We do the inverse transform, and then we for each block, and then we put all the blocks back together and output our image. And as a result, we put in our input image, and hopefully we get a good quality image on the output. But if we throw away too many coefficients, or we quantize them too coarsely with this Q block, then we start to see the degradation. So, so already we understand where all that block structure comes from, right? So you'll be able to entertain your friends at parties by sharing that that knowledge. They'll be really interested in that, I'm sure. But we've all seen that blockiness, right? And so it all comes from the block-based DCT processing. So I won't insult you by asking that, because you know that that's lossy, because it has this quantizer, right? And it can generate these sorts of images. Okay, let me just check something. Yes, I just wanted to talk about this first. There are a couple of decisions we need to make in that process of JPEG coding, and one of them might not seem so important, but it is worth highlighting, and that is the order in which you read out the coefficients from these blocks. So remember, we're segmenting our image into lots and lots of 8x8 image blocks. We perform a DCT on each one, and we end up with a set of transform coefficients which we quantize. Now, how do we then take this two-dimensional array and send it off to our decoder? The first reaction might be, well, it doesn't matter. We can just do the obvious thing and just read across the top row and the second row and the third row. But in fact, the order in which they are read out is normally a zigzag scanning pattern, as it's called, and it follows this order here, working from that top left and going diagonally to eventually get to the bottom right. Any suggestion why we might do it that way? What would be the advantage, you think, just from what you know? Yeah, very good. That's exactly right. Because we've seen that the result of the DCT is to push all the energy up into this top left-hand corner. It's not to the top line, it's in the top left-hand corner. So all of these coefficients out here, particularly when they're quantized, are going to be very small or zero. Okay? So by reading out these coefficients in this order, partly we encounter the larger magnitude ones earlier, but most importantly, we'll get to the last non-zero value earlier. So we can just reserve a special code saying end of block. Okay, so maybe if we quantized, so maybe if we transformed and quantized, maybe everything outside, say this area was zero, then we could represent each of these values in order, and when we get to here, we simply say end of block, and that saves us with the alternative of reading the first row, then the second row. There'd be all these blocks that were zero, and we'd have to communicate that in some fashion. Okay, so the zigzag scanning just saves us a few bits by getting to that last non-zero coefficient earliest. Now in the block diagram that we just left, in this one here, we had this block called Q to the minus 1, inverse quantizer. So what is this Q to the minus 1? We know we can't reverse quantization, right? We've lost information at that point. There is no way to reverse it. So it's very important that we understand that quantization cannot be reversed, but quantizers are usually adaptive in the sense that we might choose different step sizes for different conditions or different settings. So for instance, I'm sure you've all used JPEG in some application and it's asked you to input a quality factor. Right? So we'll see how that quality factor influences the quantization, but the receiver needs to know what the quantizer step size is, just the same as the transmitter. So at the encoding side, we've decided whether we're using these small step sizes or the larger step sizes, and if in a particular situation the quantized value turns out to be 2, and that's what we send off to our decoder. The decoder needs to know how to interpret that 2, whether it 2 maps onto a value here or 2 maps onto a value there. So that's all the inverse quantizer does. It just takes, it just allows the correct mapping of the value, the number here, onto the correct actual actual real-world value. Yeah, makes sense. I've included in on the LMS this DCT tool, which is just called dct.xls. And you don't have to, but I'd suggest that it might be useful to download it and just play around with it. I've got it on here, so I'll just show you what we can do with it. It's not very sophisticated, but I think it's useful in understanding the value of the DCT and also how the DCT works. So if I just take a moment to go here and change that. And so this is simply an Excel implementation of a DCT. So you see lots of some lines missing here where we take this data, perform a 2D DCT and generate these transform coefficients, and then on this second sheet here we do the reverse. So here's a set of transform coefficients, inverse transform to get back to the pixel domain, and then these 3D plots are beside. So with this particular set of data, all I've done is made up a set of 8x8 pixel arrays that could represent a reasonably deep edge or sharp edge in an image, because the intensity change is fairly, quite a lot over a small number of pixels. And we can see that if we take that 8x8 array, take the forward transform and keep all the coefficients, then this is what it looks like in that transform domain. We have a very high coefficient at the 0, 0 point. Remember, that one is proportional to the average intensity. A few high energy values at the near the origin, and then all these small ones outside. What is interesting, though, I think, is if we look at the reverse and consider what would happen if we coarsely quantized or zeroed all of these small values. And what we're interested in, of course, is this reconstruction here. So if I take a little time, hopefully not too much time, to just very coarsely quantize that transform data, we get a bit of a feel for how effective the DCT is in preserving and approximating the important information. So if I make this 0 and this 0, I'll keep on going for all the, single digit values. Maybe I'll round that to 10. I'm just doing sort of decimal quantization here. That's a reasonably large value. I'll leave that as 5. 0 all the small ones. So, although all the numbers are changing, what I hope you'll get a feel for is that the main features of that pixel domain array are not affected very much, even though we are doing some pretty dramatic quantization and throwing out most of these coefficients. And of course, if we're throwing out most of these coefficients, we're saving bits because we don't need to transmit them. So bear with me, I'll do it. Keep going, might as well finish the array at this point. So rounding to the nearest 10 or just zeroing, or 5. Just make that just 5. That's 10. 20. You can see there's a fair bit of horizontal structure here and not that much vertical, which is why we have those higher frequencies. Is that right? Yeah, I think this must be rotated. I'm not sure that I have my frequencies around the right way. Anyway, it doesn't change the conclusion here. So 5 and 0. Okay, so you saw how coarsely I was quantizing those things to the nearest 10 or the nearest 5, zeroed all the small ones, and yet the basic form of this thing has been preserved. So it just gives a feel for how effectively the energy is compacted into a small number of coefficients. The other thing that you might be interested to do, if you weren't completely clear about the basis function concept, is that we can zero all of these and just put one coefficient in to see obtain a view of what all those basis functions were. So if I put a number in here, what am I going to get in the spatial domain? If I put a number in the 0, 0, it's going to be just flat, right? It's because that represents the average intensity up in that 0 frequency point. But if I keep that 0 but move a value over here somewhere, then we get that one of those first basis functions, changing only in one dimension. Or maybe I want to remove that one and find out what the basis function looks like in the 2, 2 point, choosing a number at random really, where we get this more complicated cosine going in two directions. So anyway, that's on the LMS, and if you're interested to explore things a little bit with it, maybe that's useful. Okay, so let's just kind of double click on that earlier block diagram and look in a little bit more detail at the JPEG encoder. So we have the this of course is after the initial transform and subsampling rather. Sorry. So we've gone from RGB to YC-RCB, and we've subsampled the chrominance. Then each of those is segmented, and we perform this on each 8x8 block. So 8x8 pixel blocks go into the DCT, the DCT coefficients will be quantized, and they're quantized according to a quantization table. And we'll talk about that, where that table comes from, in just a moment. The DCT coefficients are actually encoded in a slightly different way depending on whether they are the DC coefficients, that is the zero frequency ones, or whether they're the AC coefficients. So the AC coefficients are read out using that zigzag scanning approach, and the DC coefficients are actually predictively coded. So I'll show you how we do that in the next slide. And then the resultant values are Huffman coded before sending off to the decoder. And the Huffman tables are based on the probability distribution of that particular image, so the code words have to be sent off to the decoder as well. What's this about the DC coefficients being DPCM coded? Well, you would expect that in a typical image, let's go back to our friend Lena here, we always use Lena, there would be many blocks, adjacent blocks, that would have approximately the same average intensity, would you not? I mean, there would be exceptions, right? A block here has a very different average intensity to that one, but there, as a result of the structure that we say is common in most useful pictures, there would be a lot of 8x8 blocks that would have similar average intensity. And so rather than encode each DC coefficient fresh, what's done in JPEG is that we predict based on the previous one. So instead of the AC coefficients are encoded separately, so we're looking only at the coding of these zero frequency coefficients. But when we encode this one, we predict it from that one, and we just encode the difference, and similarly this one from that one, and so on. So it's just because of the assumed strong correlation between the average intensities of each adjacent block that we encode the coefficients in this way. Now, these quantization tables. The quantization tables represent the step size, the quantization step size, that's used for each individual frequency frequency component. And we can relate that back. I'll bring up the slide if you'd like me to. But remember, in the first lecture we talked about the sensitivity of the human eye to different stimuli, and in particular we are differentially sensitive to different spatial frequencies. Remember, we had that that plot showing that we need to encode the mid spatial frequencies with greatest accuracy, and the high spatial frequencies we can maybe ignore or quantize more coarsely, and that's realized here. So these are the default quantization step sizes that are applied for the relevant spatial frequency in this 8x8 array, and you'll see that they generally increase towards the higher frequencies, as we would expect because we are less sensitive to them. And we have a different set of figures for the chrominance and the luminance, so the chrominance ones are applied to both CR and CB. And in the JPEG encoder, which was let's go back a couple of slides, we apply a scaling, a quality setting, which is which scales them, right? So in a particular software package where you input a quality factor or quality setting of 1 to 100, or in Photoshop you use 1 to 12 or something similar, then that turns into effectively a scaling factor on these quantization steps. So these quantization step sizes, or these quantization tables, have been provided by JPEG. I don't know if I ever mentioned what JPEG is. It's the Joint Photographic Experts Group. It's just the name given to the standardisation body. Now, some parts of a standard are mandatory in the sense that they would have specified that DC coefficients must be encoded using DPCM, using one-step prediction, and these are the code words that you use, or something like that. But some parts of a standard are for information, they're not mandatory, and that's the case for these quantization tables. So JPEG has said, as a result of a lot of human testing, under controlled viewing circumstances, this is a set of quantization tables that you could use if you want, but you can use your own. They are communicated with the image, so every time you take a photo and store it away in a file, there is a record of what quantization tables are used and the scaling factor that applies to each. And the easiest thing to do when you are writing a JPEG coder is to just use these default values. But for companies or applications that are highly dependent on the quality and the file size of your images, maybe you want to put more effort in. So Adobe has their own set of quantization tables, and cameras, if you have a Nikon or a Pentax camera, one of these high-end SLR cameras, they will try to optimize the quantization table on the fly according to the image characteristics and their patented algorithms that they would want to protect. So that's the essence of the JPEG coder. It involves these blocks that we would expect from our earlier discussion, with a few subtleties about reading out two-dimensional arrays, quantizing according to the particular frequency characteristics, and that differential coding for the DC coefficient. But the last image compression system I'd like to talk about is JPEG 2000, and it's not because it's particularly widely adopted. In fact, is anyone who's heard of JPEG 2000? Yeah, it's been around since 2000, but has not been widely adopted. There are a couple of reasons for that we could talk about, but I think technically it's interesting from the point of view of how the new coder was put together. So JPEG's obviously been very successful, but it does lack some features that might be desirable. One is good performance at very low rates. So JPEG is fine at fairly high rates, but as soon as you try to squish it down for high compression, we end up with that very blocky kind of appearance. It's not necessarily ideal for high resolution images because it was essentially optimized for TV resolution images. Now, of course, we use very high resolution images. Nor is it particularly effective for computer-generated images, where we have areas of very uniform colour or luminance and sudden changes or sudden edges. There was actually, it's not well known because it's not well used, not widely used. There was actually a lossless version of JPEG, but effectively it was a completely different coder. There was no commonality, so there was no common bitstream structure, and arguably it might be nice to have a common bitstream structure so that you can take out some of those bits and generate a lossy version, or take out all the bits and use them to obtain lossless compression. And in the same vein, it wasn't easy, or no, it wasn't really possible to obtain a scalable representation in the sense that depending on how many bits you save, you get an increasing or a higher quality of reproduction. So the JPEG committee, back in the late 1990s, I guess, decided to come up with an alternative, which became JPEG 2000, and they moved away from the fixed block-based DCT to a multi-resolution filtering approach based on wavelets. So at very high compression, it's not necessarily obvious to you, perhaps, depending on how far you are from the original, from the screen. Sorry, but at very high compression, as we've said before, you get this blocky structure. Maybe I didn't choose an ideal example, or maybe the overhead projector is filtering it a bit, but I'm sure you know what I mean. So the intention was to move away from the block-based representation, and in doing so, they recognised that typically images have this characteristic. So typically there are low-frequency components that extend over a large portion of the image, and actually my previous picture is a good example of this. So there are large-scale, which means low-frequency, components that extend over large parts of the picture, and high-frequency components, which define the fine detail, tend to be over smaller parts of the picture, right? Up here, detail around here, and so on. And yet, the block-based structure, the 8x8 pixel structure, always uses the same analysis window, right? It always looks for frequencies within that same block size. So that was why it was considered that maybe a multi-resolution approach might be better, and led them to look at wavelets. So what are wavelets about? Very simplistic or high-level representation of wavelets is that we have a signal, and we apply a low-pass filter and a high-pass filter. The high-pass filtered components we keep, and the low-pass filtered components in both cases we can downsample them, right, because we have a more restricted bandwidth. So we downsample the high-pass filter components, the high frequencies, and keep them. The low-pass filtered components, the low frequencies, get downsampled as well, but they can subsequently be kind of recursively filtered and downsampled again. So we have a second round of filtering and subsampling and maintaining the high pass in this case, and continuing to filter. So in an image, it means that if we take an image like that, the first step in performing a two-dimensional wavelet filtering is to filter along the rows or along the columns. In this case, the first iteration, the two-dimensional iteration, we perform the filtering in across the rows. So this is it's obviously distorted because we've only done the rows and not the columns, but this is the low-pass filtered version, and this is the high-pass filtered version in just the direction of the rows. Okay. And then we do the columns, and we end up with this representation. So we've got high frequencies, if you like, the high frequencies in both horizontal and vertical directions. This is high frequency in horizontal direction, low frequency in the vertical, and this is the reverse, the high frequency in the vertical direction, low frequency in horizontal. You can immediately see where we could save some bits, because you can probably see there's almost nothing here, But there are some high frequency components present in both of those ones. But if you remember the kind of recursive structure of the wavelet, we can keep on going with this filtering and subsampling. And always the low-pass filtered version containing the large details, large-scale structure of the image is the one that's most recognisable. But we end up with a representation of the image that's based on a very low frequency, low resolution version, plus all these high frequency coefficients in specific spatial locations. Okay. Okay. So early on, and in fact, wavelets had been known and were used, at least in a research sense, before the original JPEG was developed. But early wavelet-based coders were not very efficient because it took a lot of bits to identify the positions of those significant coefficients. So in that representation here, we need to identify not only the magnitude of these components that we think are important, but also where they are. And you know, various research efforts were made to try to encode this information efficiently, but it was no better than the DCT, and the filtering was more complicated, and so the JPEG chose the DCT as the solution. So this is another way of representing that. So this is the probability distribution of the wavelet coefficients in the high frequency subband, so they're highly concentrated near zero, but there are these important high value components that we need to identify and locate somewhere in the image array. So many coefficients are small magnitude and have little energy, so that's a good thing for compression. We can ignore them, but the few that we need to preserve, with significant energy, we need to somehow convey and communicate. And a major step forward in this was achieved by a guy called Jerry Shapiro back in 1993 with an approach called the embedded zero tree wavelet. And the breakthrough is based on a fairly simple concept in retrospect. I mean, he had the good sense to observe it, but it's based on an observation that there is very strong correlation between the zero coefficients at different scales. I'll show you what I mean by that in just a moment. And this allowed the definition of these zero trees, linking zero coefficients with their children in higher bands. So what's all this mean? It means that, I think the graphic tells us actually, these zero trees mean that if we observe that there's those coefficients at that fairly low resolution level are zero, then it's very likely that all the children following out in that tree type structure will also be very small or zero. And so that was the basis for a more efficient way of encoding these coefficients. And it's based on these zero tree structures and a successive approximation method. So the algorithm was to apply a very high threshold, so only very large coefficients would be encoded. This meant that there would be many zeros and many zero trees, right? If we apply a high threshold to say that we're only going to be interested, only going to preserve very large magnitude values, then way up here, many of these values will be quantized to zero, and that means all of their children will be quantized to zero, and there'll be very little data to needed to be represented. And then we just send the most significant bit of these coefficients that are above the threshold, and then there would be an iterative procedure. We'd reduce the threshold, revealing more coefficients, and send more coefficients and more significant bits, and loop around like that. So it turns out that because of this zero tree structure, that meant that the coefficients could be represented quite efficiently, but also it gives that scalable structure. We can just take the coefficients and the bits representing those coefficients from these early thresholds and reconstruct a version of the picture. If we want, we can add these extra ones later, and we can get this scalable representation. So it's efficient. It has this embedded encoding structure where you can get a low fidelity representation or a high fidelity representation. We can exactly control the number of bits. If we had an application where we wanted to compress our picture to exactly 412 kilobits, we couldn't do that with JPEG. We'd have to choose a quality setting. Is it too much, too little? Adjust the quality setting. With wavelets, we can do exactly that. We just keep on accepting coefficients and bits and more significant bits until we reach the number that we want. And if we keep on sending bits, then we'll eventually get to a lossless representation. So that was another feature that was an objective. Again, the reproduction of images in this environment might not be ideal, but hopefully you can see what's going on here. We've got an illustration of the two coding techniques at very low rate. Here's the original with 0.5 bits per pixel on average, of course. With using JPEG, we end up with this very blocky structure where within each block, of course, actually, you can tell me what's happening within each block in the JPEG, because we've got very few bits available. Or is the question not clear? Probably the question is not very clear. We're trying to reduce the bit rate a lot for JPEG. The quantization step or quantization interval is very large. So only the largest coefficients will be preserved, and the largest coefficients will be, which ones? Will be the very low frequency ones. So within each block here, we have a very smooth, very kind of blurry image. But because we're smoothing out each block, it's coming closer and closer to just the DC coefficient, which tells us the average. We're starting to see the boundaries between these blocks. They're becoming more and more visible, as we discussed earlier. So the whole picture ends up looking quite blocky. In the case of JPEG 2000, of course, we've thrown out information. It's not as clear as the original, but we don't have these highly visible blocks. We just end up with parts of the picture being starting to be blurry, and at very low rates, that generally looks a bit better. Here's another example. Again, JPEG at in this case 0.25 bits per pixel. Bits per pixel is just a basis on which you can compare some coding methods, and again very blocky as opposed to a bit blurry. So we could talk about why JPEG 2000 hasn't been widely adopted, and it's kind of personal view. Others might have a different view. One reason was that it had some patents associated with it with regard to the arithmetic coding. We talked about arithmetic coding last week, I think, and JPEG 2000 did use it. IBM had the patents, so everyone was a bit worried about having to pay royalties. But also, remember that JPEG 2000 came out around the year 2000, and one of its objectives was to obtain higher quality at very low bit rates. But you need very low bit rates when you have dial-up modems and very low speed connections, low bit rate connections. And that was true around the late 90s, but then we moved on to broadband internet, and so it's not so important, I think, to squeeze the best you can out of very low bit rates like this. So JPEG 2000 is an option that's often included in image processing software. I'm sure you can save Photoshop images as JPEG 2000. And interestingly, to to give a hint about something coming in the future, our future lecture, JPEG 2000 has emerged as a method for coding pictures that are used in the cinema for reasons that we'll talk about later. Okay, so more up to date though. Has anyone come across this one? HEIC? Right, yeah. So when we talk about video coding methods, and we will actually start to talk about it later this evening, we'll see that any video coding method also requires efficient methods to code individual frames. That will make sense when we discuss it. It's probably not a surprise, but we'll discuss exactly why you need to do that a little later. So there have been many advances in video coding over the years, and one of the most efficient international standards is called HEVC, High Efficiency Video Coding. And it has led to a particular mechanism or method of encoding images called HEIC, High Efficiency Image Coding, in the High Efficiency Image format. We're not going to go into the details of it. We might have the chance to look at some of the approaches when we look at HEVC, but some of its features that influence the efficiency of its coding are listed here. So one is that instead of being limited to always using 8x8 blocks, it allows for a hierarchical segmentation structure. So if part of the picture is pretty uniform, then just use 32x32, and then another part of the picture might have large variations, so we split that into 16x16s or even smaller. So it allows for that adaptation to different block sizes. It also allows for prediction within the picture. So I can give a very naive or very simplistic illustration of that with just looking at this slide. If I'm thinking about chopping up this image into blocks, right, and encoding each of them separately, well, that doesn't necessarily make sense in this case. Having encoded this block here, I could use that to predict a nearby block. We haven't done that in JPEG. We've encoded each 8x8 block independently. Well, apart from that DC coefficient prediction from one to the other. But this HEIC method allows for taking entire blocks and using them to predict other parts of the picture. It also allows for directional prediction. So what do I mean by that? I mean that, let's use a picture as an example, usual one. So in this case we have a particular structure to the image along this direction, and the HEIC coder allows us to predict it. So having encoded this part of the picture, we can characterize the structure as being in a particular direction and use that to predict a neighboring component. Essentially, any time you can predict a component in an image, you will save bits by just sending the difference. The flexible file format is just allowing you to do different things more flexibly than with JPEG. For instance, back when JPEG was developed, there was no concept of having a burst of images that you can take with a modern camera phone. What's its performance? Roughly about 50% of the file size compared with JPEG, so that's why it's attractive, and that's why it was adopted by Apple since I think we're not that's one generation behind, I think, in each case. But internally within Apple systems, they use this HEIC format. As far as I know, whenever you export a photo from iOS 11 or iOS 10, 12, are we up to 12 now? Can't remember. it converts it to JPEG just for compatibility with other utilities. And I'm not sure how widely it's adopted elsewhere. I'm not sure if Samsung uses it. Anyone know? No? Okay, doesn't matter. Okay, so that's largely completed the discussion about compressing images, or compression generally, and particularly looking at images. So the next thing to do is think about compressing digital video. And so in the case of video compression, we want to again exploit similarities or correlation, not just within a picture, but also between pictures. Okay, so which is maybe an obvious thing to say, and perhaps you can you're already thinking how we can do that in along the direction of the frame samples, and the same conclusions from information theory that we talked about earlier apply, and I think I just said this though. So anything we can do to decorrelate, that is, so we can't guess what the information is that's describing the video frame, will lead to more efficient use of bitrate, and that's what we strive to do. And we want to exploit not just redundancy, but also irrelevancy in both the spatial and the temporal dimensions. So if we're not sensitive to changes in the time dimension, then why send that information? So if I'd finished this slide deck at the end of an evening, I would give you this to think about, but as it is, I'll give you 5 minutes to think about it when we go to break. So think about how we could exploit similarities between video frames. If the subject's still, it's probably pretty obvious, right? We can look at differences, pixel differences. But what if the image is moving, or what if the camera is panning or zooming? That makes things a little bit more complicated. So give that a little bit of thought while you take a break. In this slide pack I include, I'm not going to go through, but I include this checklist that we talked about before. Won't go through it. And I have one other exercise that you might be interested to just have a look at to explore a little bit further this issue of JPEG. So sometime over the next week, can you try to find some time just to take a photo and just have a look around on the internet to see what utilities you can find that can tell you something about the JPEG compression. So finding resolution is easy, right? You just look for file info about an image, but can you, for instance, find the quantization matrices, or what other stuff can you find in the what other things can some utility tell you about a JPEG image? Just might be useful to find and share on the discussion forum, if you would. So why don't we take 5 minutes break, because there's a natural break between slide packs, and we'll continue talking about video. Discrete cosine transform. Yeah. It's
Can you show me on the slide?
Sure.
So it seems all the information is on the left top corner.
That's right. So remember where is it? So mathematically it looks like this. It's a bit like the Fourier transform, but instead of having a complex exponential here, we break the signal down into a sum of cosines. But the effect is to do this. This is a bit graphical, but anyway, that when we chop the picture up into segments, like 8 by 8 pixels, we transform each, then it has this effect that it decorrelates the signal. You can't guess one value by knowing another, and it concentrates the energy up into the low frequency coefficients. So when we looked at, when I used that Excel program, we saw what the result was. We can zero all of those small coefficients, and it has very little effect on the
So these picture is in frequency domain.
In the frequency domain, that's right. Yeah.
So we can recover it to the original.
Yeah. So where's the diagram? So which is what we're doing here, right? So we segment the picture into blocks, take the transform, we throw away all those tiny little coefficients, saving bits, and then we do an inverse transform and put all the blocks back together.
Okay, so the signal here is in frequency domain.
Yes, that's right. So everything from here to there is in the frequency domain. So we transmit quantized frequency domain coefficients.
Thank you.
I'm sorry I'm late today because I have a meeting with Master.
Oh, right.
It should be ending an hour. And
No worries. Thanks for letting me know.
I would like to talk with you about my project topic.
Oh, yeah.
Actually, I'm interested in human-computer interaction, and which you listed RMS. And I was wondering what should I do if I hand a draft to you?
Well, best thing to do would be to, if that's your area, do a little bit of reading and put together a structure,
paper.
or like a content, right? So we have some structure to it, what you think you can put in, and then send it to me and we can talk about it.
So I send to you by mail? Or?
Yeah, just by email.
Okay, so, and I'm a little confused about JPEG and what you told before. And why does JPEG has a better image, a high quality?
Sorry?
Why does JPEG has a better high quality than HEX version?
Sorry, I don't understand.
Actually, the DCT version has a lot of limits, and what does the JPEG overcome that?
Sorry, what are we overcoming?
So you told us about two methods of the...
Oh, JPEG and JPEG 2000?
Yes.
So is it this one?
So what's the difference between JPEG and the newer one?
Oh, so JPEG 2000 is based on the wavelets. So it doesn't chop the picture up into 8x8 blocks,
Yes.
but instead it does this decomposition. So we've got a representation of the whole picture at different resolutions with different frequency components. Right? So there's no 8x8 block structure here.
So is the JPEG 2000 perfect one? The same as original one?
JPEG 2000 is structured so that if you keep on receiving more and more bits, you'll eventually get to a lossless version. But you can also terminate early and get a reasonably good quality picture, but compressed.
Okay.
Yeah?
Yes, thank you very much.
That's right.
Could we add some like data or pictures?
Oh, absolutely. Yes.
About the model exact. Do we know like the Huffman coding, we should exactly know how this Huffman how it works.
I won't be asking you to create a Huffman code. Just understand the principles.
If we just scan zigzag like this, why would we I just
Because just wait for a second. If I show you this, and I just go back to see this was our block of image data, 8x8 pixels. We transform into this domain. Then you can see that if we suppose we wanted all the coefficients, I haven't got a pointing stick there. Suppose we wanted to keep all the coefficients up to this one, because that's a reasonably large one, right? 14.75. Right? Now, if we just scanned left to right, left to right, left to right, left to right, and we quantized so all of these small ones were 0, then we would have to send, we'd be on the 5th row of pixels, of coefficients before we got to this one here. Okay, so we'd have to be sending a lot of information saying, or we'd be using bits to simply say that this coefficient is 0, this coefficient is 0, this coefficient is 0, this coefficient is 0. We can use Huffman coding to do it more efficiently, but nevertheless we have to define all of those zeros. By scanning in this zigzag order, then because the largest magnitude coefficients are up in that corner, it means we get to the last non-zero coefficient earliest. Yeah? So maybe we only send about 8 coefficients before we're up to this one. Whereas in the other case, we've done lots of rows, several rows. Does that make sense? Does that help?
Could I just understand like this? If we want to like make a picture, and if we want to do some more useful things because we want to save bits, so this is more efficient way to save bits.
Yes, because we get the largest magnitude coefficients earlier, and so we'll be able to. So earlier we'll be able to just send a code that says end of block. All the other coefficients are 0.
Another thing is I want the DC and AC coefficient. I don't know what.
Oh, we talked about them earlier. Where's the... I'm sure we talked about them. Here. Right, the DC coefficient is just the 0 frequency, 0, 0 frequency term, and all the others are AC coefficients.
Here, the 2000 and just a GPG, the difference is just like this. Need we know how the embedded zero trees works? Like, I just know like this is original and this is their like sub pictures. This here is all 0. We know that it's enough, right?
Oh, you're saying in terms of exam or whatever? Yes, yeah.
Just because the difference is here is a blocks and
there it's just smooth.
yep. Okay. Thank you.
One is the Q minus 1. I'm not quite understand the Q minus 1 because here is the Q here means the numbers around here will be quantized to 2.
Yeah.
So we transmit 2 to the decoder.
Yep. But in this case, if we use this quantizer, then that would be number 1, that would be number 2, number 3. So, and we would transmit 1 or 2 or 3 to the decoder.
Yeah.
So the decoder needs to know if it receives number 2, does it correspond to this level or does it correspond to this level? That's all. So it just needs to know what these points are, how it needs to map back to an original value.
How they come back to the number
Yeah.
because it is the number around here.
Maybe we've got another.
For example, if there is 36 and it is 36 not 37 and it's also be quantized to 2.
Yep.
How do we know the 2 from 2 to 36?
Yeah, that's
not 36.
Oh, because we have we've sent the Q step size equals 37, for instance. We've sent that as additional information to the decoder. So it knows that it's a bad example, but I can't make the numbers make sense,
Yeah,
but
yeah, yeah.
you know what I mean, right? It needs to know that number. It needs to know what that corresponds to. It needs to know what that corresponds to. It needs to know, right? So when it
So the steps will be the same. Therefore,
well,
we can.
then in general, quantization steps don't need to be the same, but they are in JPEG. They use
Then we'll use the number and the steps to.
yeah,
Okay.
just to do that inverse operation.
Okay.
Okay, so let's get going again. Hopefully you've got the answer. You've been thinking about how to encode video, and I'll just confirm what you were thinking. This is what we will look through in this topic, this video compression topic. We'll look at some additional tools. We've looked at some in terms of general compression and image compression, but we'll look at what other things we can do that are suited to video compression. In particular, we'll look at interframe coding using prediction. So I already sort of hinted at the idea of predicting one frame based on another. And we'll develop what I'm calling a basic video coding architecture. And I'm calling it that because any and all video coders that are used today essentially have this one fundamental basic architecture. They change some of the parameters, and some things can be done more flexibly and with more options, but the basic coding architecture is the same. We'll look at how we can improve prediction. Improved prediction always means reduced bitrate. And we'll look at the evolution of some of the standard video coders that you might have heard of. You might not have heard of this one, but you've probably heard of MPEG, MPEG-1 and MPEG-2. They're a little bit historical now. MPEG-2 is still used in TV transmissions, for instance, and on DVDs, but they're not the most efficient, most modern ones. But there are two reasons why I'd like to visit these, at least briefly. One is because they are simpler, it's easier to see the basic structure, the way they're put together. And secondly, if we look at a little bit of the historical development from one to the other, we can understand why the different coding tools have emerged as they have. So I hope that makes a bit more sense later on. But let's start off by looking at these additional coding tools, and in particular interframe coding. So the obvious thing to do if we have a series of images that don't change very much is to code the differences between these frames, right? That was probably going through your head as soon as I posed the question at the end of the previous slide pack. And the simplest form of interframe prediction, so it sort of sounds it's kind of fancy name, but all it's doing is predicting from one frame to another. The simplest way of doing that is something called conditional replenishment, which again is a kind of fancy sounding name for something that's really simple in concept, and that is just that we can segment our new frame as it arrives, and we can compare it with the old one, the last one that we've just reconstructed, and we can categorize it into two categories. Either this is almost the same as the last, as this block in the last frame, so I won't bother coding it, or it has changed and so I need to update the information in some way. Okay, so very simple in concept, but it can potentially save you a lot of bits, particularly in my carefully chosen example there, where the sky hasn't changed probably very much in that particular part of the picture over the last 40 milliseconds, which has been or 50 milliseconds, whatever. So the first thing we can do is we can just decide, has the picture changed enough to warrant coding it? Then if it has changed, how do we do it? Well, one thing we can obviously do is look at frame differences. So we've got one image at a time t, we've got another image at a time t plus 1. Things have changed in between. The table tennis ball has been hit off the bat. So we can take a difference between those two. So in terms of encoder and decoder operation, we can say that our new picture comes in. We can compare it with the previous picture. We can subtract the previous picture. We end up with a difference, and it's the difference picture that we transmit to our decoder. Our decoder has reconstructed the previous picture already. It's already maybe displaying that, and so we just have to add this difference picture and generate the new one. So does this process remind you of something that we've already talked about? Which is, it's like DPCM. DPCM is sample by sample prediction. This is exactly predictive coding. It's just that it involves entire pictures in the way I've described it here. So simple in principle, a bit of processing involved, but hopefully the statistics of this difference picture are such that we save bits compared with sending this new picture independently. And we can see that a lot of this difference picture is grey in this particular example. Where is it not grey? Well, it's where there have been the big changes, where the table tennis ball has moved. Now, I actually think this sequence involves some zoom, because all of the edges come up as differences. So already we are led to a basic video coding architecture. So to follow a recipe, if you like to build a video encoder, we start with an image coder, which we've seen essentially look like this. We simplifying and taking out things like the subsampling and the segmentation. What we do is take the DCT, quantize it, and assign code words. But we want to add to that an estimate of the current picture to do this predictive interframe coding. So if we can estimate the current frame somehow, then all we have to encode is this prediction error. And so if a lot of the prediction error signal is very small, it'll have just a few DCT coefficients, and hopefully we save bits. We already talked about this this issue, so I'll just talk through it rather than ask you to answer these questions, but just let me know if it's not clear. So what's being asked here is how do we obtain our estimate for the current picture? Do we use the previous picture from the input? And it raises exactly the same questions that we discussed with regard to predictive coding, and that is that the decoder has to make its prediction based on the quantized data that it will receive. And so the decoder won't have these original images available, it'll only have quantized data, and so it has to base its prediction on that data, and so the encoder has to do the same thing, because if the encoder and decoder have different predictions, then they will come up with different prediction errors, and the decoder will effectively get out of sync with the encoder. So using two coding in here, because I mean we use the code word, the Huffman code word in there, and then we're gonna use predictive coding too. Yes, well we've got Huffman coding there. That's the code word assignment. That's Huffman coding, and this is undoing the Huffman coding. So we can kind of say that from that point to that point is transparent, assuming there are no transmission errors. I mean, the Huffman coding does prediction too? No, the Huffman coding simply assigns code words. Right? So if you have a series of symbols that you want to represent, such as quantization levels, the Huffman coder will assign a variable length code depending on the probability of the symbols. But it won't, Huffman coding by itself will not do predictive coding.
So I meant, are we using two coding schema in here, or like are we using two coding method in here, or isn't it enough to use Huffman coding? Or this video encoder? Okay. So you mean this in video encoder include Huffman coding
Yeah,
and
yes.
predictive coding?
Yes, that's right. Yeah, sorry. So this is the predictive, if you want to break it down into its elements, we've got the predictive step here, generating a prediction error signal. We're then compressing that prediction error signal using the DCT to concentrate the energy into just a few coefficients. And then when we quantize that, we're also using the Huffman coder to take advantage of the statistics. Yeah? I should have made that clear. So we, and this logical development is the same as I talked about earlier, but we're saying that we can't use these previous input frames because they're not available at the decoder. We have to use the quantized information, but we can't directly do this for the same reason that we discussed in the case of DPCM, and that is we're trying to predict a full. We're only using the luminance component just to illustrate, but we're trying to predict a full image there. So we need a full image here, but the signal that's generated after the subtraction is a difference image, and we will represent it as a series of blocks of DCT coefficients. But when we get back to here, it's still a difference image. So we can't just delay it until the next frame and use it to predict this picture directly, but rather we need to get back into this pixel domain instead of the difference domain. Does that make sense? If it's not completely clear, just wait for. Sorry. So this fixes it. It was a logical. We went through the logic in the discussion about DPCM, but if it's not clear, tell me. The scenario I was presenting to you was if we have to use the quantized data to form our prediction, is it simply a matter of taking that quantized data, getting back to the pixel domain and using that data directly? Well, no, because this is not going to predict that. This is a difference picture. We need to get back into the pixel domain. We need to add that to our previous picture to generate the prediction, and that's achieved in the same way as we saw the prediction loop in DPCM. And I can illustrate that again with some little thumbnails. So this is the new image we want to predict. We've got to generate this one. We have a prediction error that results. Via the transform, we get back to prediction error here, which looks like this. We have to add that to our previous frame to generate a prediction for the next picture. Okay. And we see in there that we've actually already got a decoder. It's not only not uncommon, it's essential, really. In any quantized video encoder, we must include a decoder because we've got to create this same prediction that was used that is used in the decoder. So if we take away those components, this is a full decoder. We are reconstructing images here or here. We take in the quantized data from the encoder to do it. So if we just take those graphical components and just rotate them and reorganize them a little bit, then we get the structure of the decoder. Okay, so the decoder receives a quantized representation of a difference signal. I might have my little thumbnails here again. Yeah. So this is a different signal here. It's added to to the previous frame to generate the new one. Okay. Happy? Okay, so that was all just generating this, which, as I was saying, is this basic video encoding architecture. So we will see how there are different variations about block sizes and how we do this prediction, but this architecture, this prediction loop, is the core of any modern video coder. In fact, I'll pull out a picture from one of the standards shortly, and you'll see that it's exactly that diagram is reproduced. So let's move on and think about how we might be able to improve this prediction. We've seen that maybe if we do interframe prediction, just taking differences from one frame to the next, we might be able to obtain some advantage. And it will work well provided nothing moves or nothing changes. But what if something does change? We would ask ourselves, can we make a more sophisticated prediction of the new picture based on the previous one? And indeed we can. And maybe a hint about how we can do it might be obtained by just going back to an earlier diagram, which is this one. Let's think about how we were saying, let's encode this picture as this one plus some difference. But you can see what this difference signal actually says. It says we've got to subtract the presence of the table tennis ball in this location and add it back to this location. But if we step back and look at these two pictures, we can say, well, this might not be an ideal example, but we can say, well, we actually got information about that table tennis ball, so why do we have to reconstruct it in another place here? Couldn't we somehow take that information about the table tennis ball and shift it to its new location? Yeah? I mean, without knowing quite how we're going to do it, logically that would make sense. We shouldn't need to redefine those pixels because the information's already there. And indeed, this is the basis for a very important technique in video compression, which is called motion compensation. And maybe the name sort of gives away what it does. It tries to compensate for motion, for changes in the image. So, what's motion compensation all about? Let's explore it by way of example. So here we have two frames. We're about to encode this frame, and we've already encoded and sent frame n-1. And suppose we're segmenting up this picture, and we are trying to predict this block from data in the previous image. But if we went to just those same pixel locations, so the same coordinates, we see that we might get a reasonable prediction for much of this block, but we could do better, possibly. In fact, the information, or the pixels defining the eye of the fish, are present in that earlier picture, they're just not in the right location. So what we can do is search nearby. Okay, so we actually move a block, we do a search for a block nearby in this location in the previous frame until we find a better match. And we find the best match of our options is shown there. Now that's all very well, but having found it at the encoder, the decoder needs to know to shift those pixels and use them for the prediction as well, right? So we can't get away from the fact that we need to send some side information, and that side information is called a motion vector. So, so when we encode this block of pixels, we're going to send to our decoder a couple of coordinates saying, you've got to go to your previous frame and translate the block of pixels that are 3 pixels down and 2 pixels to the right, shift that, use that for your prediction, and then I'll send you the prediction error. Yeah? That's basically what motion compensation does. So it requires this motion vector to assist with the prediction, but despite the processing, you might already be thinking, well, that's maybe a lot of searching to do. Despite that processing load and the fact that we have to send these additional motion vectors, if we can get a good prediction, then potentially I can just send those two numbers, the horizontal and vertical shift, and I might be able to avoid sending any more data if the prediction is a good one. If the, in particular, if the motion was pure translation over a short distance and the lighting doesn't change all that much, then I can potentially save a lot of bits, and indeed we do. One thing that can sometimes confuse people when first introduced into this about motion compensation is thinking that there are going to be gaps somewhere because of shifting blocks. But so I hope this slide shows that that is not the case. If we're predicting this new frame, maybe block A is best predicted by this one, which is in the same location. Block B has to have something a little bit offset, and so on. So as we work through here, you'll see that for each of the blocks in this new frame, so this is the new one that's encoded, we have to take slightly shifted blocks from the previous one. But even though, you know, this previous frame has already been reconstructed, we've got all the pixels, and it doesn't matter that this we're maybe not using all the pixels from this previous frame. The important point is that there's no gap in between any of these. Right? We are simply telling the decoder to use this block of pixels, shift it a bit, and they're our prediction for this block. So there are no gaps. Yeah. Maybe you didn't think there were going to be any gaps anyway, but I just wanted to make sure that was understood. But there is the question about what we do if we can't find a match, or how do we handle the edges of the picture, for instance. So there are a couple of things we can do. We could just, for instance, if the ignoring the fact that this part of the prediction would come from outside the frame, we might find that because of the particular motion that occurs in this lower right part of the picture, our ideal match would be a block that's offset right outside the frame. So there are different ways of handling that. We could put constraints and say we can't search outside the picture frame, or we can try to interpolate and guess what's happening out there. And we're going to, we might come back and revisit that a little later. But for now, let's just focus on the motion compensation process. So now we have just a slight variation on what we talked about earlier. We've got our two frames from our table tennis sequence. The different signal without motion compensation looks like this. The different signal with motion compensation looks like this. Okay, so we've been able to translate the image of the, or largely translate the image of the table tennis ball. It's not perfect, so we still do have some difference signal here. But we've also been able to translate the parts of the picture that we're describing, the edge of the poster on the wall and the edge of the table, so that all of these different signals have been reduced in magnitude quite a lot. Yeah? But
we do have to send this field of motion vectors. So for every block that we encode using motion compensation, we've got to transmit a motion vector. And actually you can see that these motion vectors all tend to be pointing outwards or inwards from the middle, which suggests that the picture is zoomed. Okay, so if we're going to generate motion vectors, it means we have to do matches of these blocks of the image. So it's a pattern matching task. There are different search strategies that we could use, and we'll talk about them in just a minute. About how, just computationally, how we would find the best match. And we also have different criteria that we could use to decide when we have a best match. So the obvious thing to do might be to, for each of the blocks that we tried when we did this search, we could find the mean square error between all of those pixels and the one that we're trying to match. That would be an obvious thing to do. But it does involve quite a bit of computation. So maybe an alternative might be what's called MAD, minimum absolute difference. So we just take the difference between all the pairs of pixels, take the absolute value, and add them all up. It's just computationally it might be a little bit better than mean square error. Anyone have any thoughts about this? If we minimize the error, will that necessarily lead to minimum bits? No? Why do you say?
It'll be the closest to the original uncompressed video, but that doesn't necessarily mean that we've sort of file size.
Yeah, that's right. So on average we would expect the smallest error to lead to minimum number of bits, but ultimately it depends on the particular statistics of that different signal. So there's no guarantee. It's not completely deterministic. Okay, let's look a little bit about how we can do this searching. So the most obvious thing that you could do if you're trying to perform this motion estimation would be an exhaustive search, and that's the way I described it at first. So I don't know if you can see that that grey block there, but if assuming we constrain our search to within a particular window, so we've got a block of pixels that we're about to that we want to encode, and our block exists in that corresponding location in the next video frame, if that makes sense. Picture I'm trying to paint here makes sense. And so we go back to the previous frame and we search within some defined space. We wouldn't search over the entire picture just because of the computational load, but we would define a search window and we would search within it. And so the search window is defined by the grey. And so an exhaustive search, as the name suggests, would mean that we would just try every location. Right? We go up to the top left-hand corner and we calculate say a minimum absolute difference, and then we shift by 1 pixel, and we shift by 1 pixel, and eventually we get down to this bottom right corner, and we look at our list of whatever it is, 256 different locations or something, find the minimum of our difference measure, and decide that that is the best match. Okay. So this an exhaustive search method would guarantee us to find the best match, of course, because we've tried everything, but of course it's computationally very demanding, and so commonly we look for ways of accelerating it, and one way is a technique that has various names: 3-step or telescopic or logarithmic search. And the basis of this one is that we don't exhaustively search every possibility, but rather we assume that the difference measure will change only gradually across the image, and so
So we try selectively. So we look at 9 possible matches. Why 9? Well, we take the centre one, and then we do upper left, upper middle, upper right, left, centre, right, lower left, lower centre, and lower right. And we find the best of that set. Okay, that's not our final location, but that's our new reference from which we try to zero in. We try to then search more accurately. So with this revised reference location, we are going to do another search, but on a finer resolution. So now we search the 9 locations that are nearby this revised reference point, and so on. So we can keep on doing that depending on the resolution that we need. And so this won't necessarily guarantee us the best match, but it's reasonably likely that we'll find the best match, unless there's some very detailed and complex content of the block, and it's moving in a particularly strange way or something. Does that make sense? The process makes sense? Yeah? Okay. Now another technique to obtain, or possibly obtain, a better estimation, even more accurate estimation, is what's called subpixel motion estimation. And I think the best way to understand subpixel motion estimation is to look at a one-dimensional example. So if you try to imagine this one-dimensional image or signal, that we're trying to do the same thing as we've just described, but just in a one-dimensional sense. I hope this will explain why subpixel motion estimation makes sense. So let's suppose we have this original analog function, so a varying intensity field that we're capturing with a camera, and the camera is doing sampling, right? So we sample our intensity field at a series of points, and then in the next frame time, so remembering, although I've got a one-dimensional example here, remember our analogy is video. One frame time later, we're capturing exactly this, almost the same function. It just happens to have been translated by some distance. So our motion estimation task is to try to shift these this set of samples relative to this one and try to get the best match. Does that make sense? Right? We're trying to predict these samples based on these ones. So we're wanting to, in fact it's the other way around. We're trying to shift these ones in time and compare them with these and try to get the best match. But because of the particular instance at which that function was sampled, and I've carefully chosen, of course, to illustrate this, it's not necessarily such a great match, because we happen to have sampled that slope in the middle here and down near the bottom here. So it might be difficult to get a really good prediction of these samples based on this one. And that's, in the end, what we want. We don't care what the actual motion was, like how many pixels have been moved. All we care about is taking our previous data and obtaining the best possible prediction of the current data with some with the included parameter of the motion estimation. So this time let's go through the same process, but allow for the possibility of just estimating the half sample points. So this is where the subpixel comes in. So as well as attempting to find a good match for the original sample points, let's also allow for the possibility of interpolating and generating these intermediate points and doing a search on that. And because of the particular points on this example, this artificial example, you might see that we're likely to get a better match in this particular instance. So this has nothing to do with not sampling often enough, right? It's not that it's there are Nyquist sampling issues here. It's simply that the particular points on which we have at which we have sampled our function aren't necessarily lined up in those two time instants of the earlier slide here. The sample points here, compared with the original analog function, are not necessarily aligned, and as a result we won't necessarily be able to get a really good match. But if we start interpolating in between, we might be able to get a better one. We might not, but we might. And so sub-pixel motion estimation allows for that possibility. Despite what you might be concerned about, which is the additional processing involved. So, and it gets back to that same philosophy I've repeated, that almost without exception, any way that we can improve our prediction always gives us some benefit. So, what does sub-pixel motion estimation mean in 2D with an actual image? Well, these are our pixel locations, our integer pixel locations, if you like. They're the actual pixel locations. And we would go through a conventional motion estimation search, and we might find that, we might find that of the integer pixel locations, this is the best match that we get. Okay. And but at that point, we don't necessarily stop. Then we say, well, okay, we'll just do a simple interpolation, and we'll estimate what the half pixel locations were, and we'll do another stage of searching just nearby. And we might find that there's actually a better prediction if we use that set of data. So it doesn't matter that that set of data didn't originally exist, or that we formed it by interpolating. The fact is that if we tell the decoder to interpolate these half pixel locations and use that for the prediction of our block of pixels in the next picture, we actually get a better prediction. Yeah.
How do we get a half pixel location?
We can just simply interpolate. So this pixel would be the weighted sum of these two pixel values, and this one would be the weighted sum of these four. That sort of process.
Does this happen in the encoder?
Yes, because getting back to the original point, or an early point I made, is that the encoder and the decoder always have to make the same prediction, and the encoder includes the decoder inside. So yes, the encoder has to do this interpolation to generate the half pixel locations and do the matching to see if it can get a better match. It might not, right? It might try these half pixel locations and decide that this red block location was actually the best, and then it will tell the decoder that the motion vector is 3.5 pixels vertically and 2.5 pixels horizontally or something, and the decoder will know that it needs to interpolate into the half pixel locations and use those for its prediction. And it can be taken beyond that. Quarter pixel locations, quarter pixel motion estimation, or even smaller, is actually used. Right. So, is everyone happy with the sub-pixel motion estimation? Yeah. Good. So a design decision in our encoder might be how big should the blocks be when we are doing this motion estimation? What do you think the trade-off might be between using large blocks and small blocks? So these are not DCT blocks, these are motion estimation blocks, motion compensation blocks. would be good about large blocks or good about small blocks?
Maybe large blocks we need to send less data, more compressed.
Yep.
But,
Yeah, if we have large blocks, then we have fewer motion vectors. We have to have a motion vector for every block, so we're saving some bits. Yeah. What about the small blocks?
Maybe small blocks are the moving parts and large blocks are just steady part.
Well, yeah, you're going several generations of coda down the path, so well done. Yeah. Which do you think is more likely on average to give a better match?
small blocks.
Small blocks, right? Because
More details.
yeah, more detail. So this guy's leg might move in one direction and the grass will stay unchanged. So we can't capture that with one large block or one large block here, but we can if we split it up into smaller ones. So the small blocks will give us greater accuracy, so a smaller prediction error, but we'll have to send more motion vectors. Yeah? And in fact, to anticipate where we're going, later generations of coders found or included the possibility of representing these blocks hierarchically. And so if we could use a large block, we would. But if we were here and we wanted, because the motion across the block or the changes within the block were different, we could split it down into some sort of a hierarchy. But we'll get there next week. So we talked about that. What about the search area that we should search in? Because this is another design decision we'll have to make. If we're encoding this, this is our new frame based on previous data. So let's start with a kind of a reference. We're about to encode this block. We're going to search. Do we search within this search area, or should it be larger, or should it be really large? What do you think the trade-offs might be there?
I think this one is like there will be a delay in transmission. Delay because it keeps searching.
Well, maybe it's a delay, but there's certainly more processing involved, yes. What else?
What was the question?
Pardon?
What was the question?
Well, what are the issues or trade-offs? What do you gain from using a large block, or lose by using a large block? Now you mentioned there's a penalty if we have a large block. There's a lot more processing because we're going to do a lot more searching. Would there be any?
Quality maybe weak, not good quality.
Which way?
Like the quality, I mean the position of the blocks of the pictures. Like it's not like more details or.
No, we're using the same resolution. It's not more detail, I don't think, unless I'm not understanding what you're saying. Are we more likely to find a match with the larger block or the smaller one? Larger search area or the smaller one?
Small.
Why?
Because the motion vector is smaller and lower bits.
You're right, except there wasn't was the answer to the wrong question, I think. But in terms of finding a good match, are we more likely to find a good match with the larger search area or the smaller? Pardon?
The big block.
The bigger one, right? Because I mean, this is highly artificial, but in this case, we've been able to find the table tennis ball where we couldn't in these smaller ones. So, and if so, we could say that a larger search area would always include the smaller one, so we couldn't do worse. We might find a better match if we allow for a larger search area, but A, it involves more processing, and oftentimes we might find that large processing comes with little benefit because the changes are not that great. But secondly, if we have to define motion vectors that are larger, then we're going to require more bits, which I think is the point you were getting at. Right? If our motion vectors are just, say, plus or minus 16 pixels,
and that requires a certain number of bits. We'll probably Huffman code them, but anyway. But if they have to be plus or minus 128 bits, we need more bits to represent them, so greater accuracy. So more bits would need to be transmitted. And so there tends to be a compromise here as well, and for most coders it's well, in early coders they tended to use 16 by 16 blocks, but that has become more flexible as well. So here I have a bit of a table of some of the trade-offs of motion estimation. I was going to talk about each point, but we've talked about some of them already. Let's talk about this one. The number of vectors per frame. If we decrease the block size, so we're doing. So this is this picture. Right? If we're using these blocks, smaller blocks instead of these blocks, what does that do to the number of vectors per frame? It increases it, right? What if we increase the search area?
Yes. This one.
Yeah, the number of vectors per frame stays the same. It stays the same, right? We've changed the size of the motion vectors might change, the quantity, but we've only got one per block. And if we use sub-pixel motion compensation, does the number of vectors change? No. It's again we have more accuracy, so we've got an issue of motion vector values, or the range of motion vector values increases, but we've got the same number of vectors per frame. Before I reveal my answers, are there any others of those that you'd like to discuss? Easier just to see what the outcome is. So, in terms, I didn't realise I'd done this. In terms of computation, if we decrease the block size, I don't think it's immediately obvious, right? Because yes, each search involves fewer operations, but we've got to do more of them. So I'm sure another level of analysis would reveal what the trade-off is, but it's not immediately obvious, I think. With increased prediction accuracy, with the, we're still in the decreased block size thing. With smaller block sizes, the prediction accuracy increases. We talked about that one earlier. The range of motion vector values increases. That's not true, is it? It depends on the search window. Yeah, so I'll have to correct that. The number of vectors per frame increases because we've got more blocks. If we increase the search area, then the computation increases, of course. Right? Got to do more matches. The prediction accuracy can't get worse, so it may get better. The range of motion vector values increases because we have we need to define a larger range of pixel numbers, and the number of vectors per frame doesn't change. Right? We're changing the area in which we search, but we're not changing the number of blocks in the frame. So the number of vectors per frame it stays the same. If we introduce sub-pixel motion compensation, computation certainly increases, right? Because we are having to do all that interpolation and do another layer of matching. The prediction accuracy, will that increase, decrease, stay the same? Increase. It'll increase, it'll improve, won't it? Otherwise, that's the whole purpose of doing it, is to try to get an improved prediction. So that will improve. The range of motion vector values
will increase because we need to specify our motion vectors to sub-pixel accuracy. Right? So we don't. A certain number of bits would be required to specify integer motion vectors. Now we're going to fractional motion vectors. And the number of vectors per frame, is that changed by using sub-pixel motion estimation? No, it's not. Right? The number of vectors per frame is locked to the number of blocks that we use. So decreasing the block size changes it, but just searching in different ways doesn't change it. Okay, so I said I wasn't going to go through each of those cells, but I did. Okay, so now with our newfound tool, this motion compensation thing, we need to change slightly or update our standard encoder architecture here. So what needs to be changed? Any suggestions of what needs to be changed? Not major changes. Really, we're being more. For a start, we're more specific about prediction. We're doing motion compensation here. So our generic delay and prediction can be replaced by a frame store because we're doing one frame delay, and our prediction is replaced by motion estimation and compensation. That's the right. So that's all very well, but what else is missing, do you think? There's something missing here. We now have to send something else to the decoder. What's that? The motion vectors. That's right. And we also need to do our prediction somehow. So we need to compare our new block of image pixels with what's available from the previous frame that we know is also available at the decoder to obtain our match. So we need to obtain that source as well. Now I went to a lot of effort to emphasize that when we were doing predictions earlier, we couldn't take information from this source because it wasn't available to the decoder. Why is that acceptable, or have I made a mistake?
Because we send it.
Yeah, that's right. Motion estimation is not done at the decoder, right? The motion vectors tell the decoder which blocks to translate, but it doesn't have to do a search. So so it doesn't need this reference picture available. So we're perfectly fine doing it just at the encoder. The decoder has obvious changes, which are pretty minimal. We have a frame store instead of this generic delay. We have motion compensation instead of prediction. Note that it doesn't say motion estimation because motion estimation is not done at the decoder. And the thing that's missing, same answer, is the motion vectors, right? We need to receive those and use them to do our motion estimation. And, motion compensation, because I've said it multiple times, no motion estimation at the decoder. Okay, so let's look a little bit historically, but don't discard it as being irrelevant to today. I'd like to look at where some of these, or how some of these standard video coders emerged, and you'll see some familiar diagrams as we go through some of this. First of all, a word about the standardization process. There are a number of relevant standards bodies, but the two most important ones come from the ITU, the International Telecommunications Union. The T stands for the telecommunications sector. And there's a video coding experts group in in that area, and they all the formal bits are there, but their responsibility is focusing on telecommunications applications, of course. So they're particularly interested in low delay applications, on error resilient applications for use over networks, and for things like video telephony and video conferencing, these sorts of things. That's why they looked at standardizing video coders. In some ways they have worked historically in collaboration with this other group. Some would say they worked in competition, but I think there's an element of both. But in the ISO, so the International Standards Organization, the IEC is the International Electrotechnical Committee. Don't worry about the acronyms too much, but this is these guys, the ITUT, comprise all the telcos, so people like Telstra and Optus from Australia, and AT&T and BT, Singapore Telecom, all of these people contribute into the ITUT. These guys are composed of, or contributions come from the national bodies. So in Australia's case, it's Standards Australia. Standards Australia will coordinate the inputs from any interested company or committee of companies. So again, Telstra might be interested, and Telstra did contribute to this group, but it ends up being an agreed country position, Australian position, and is so it's a Standards Australia input. And so, why are these guys interested in video coding? Because it's covered up there, right? Well, in fact, their interest is in more generic applications. So they started developing standards in this space because they were interested in computer interaction and stored applications like DVDs and so on. But obviously the two intermingle. Once you've got an effective video compression system, then why not use it for telecommunications applications as well, or vice versa. So as I say, they largely worked together, and many of the standards have been released by both bodies. They just appear in two different documents with two different names. And yes, the demarcation between them is not always clear. There are also industry forums, and they are becoming increasingly important. So what's an industry forum? It's when a group of companies get together and they decide that they need to agree on what they'll call a standard, but it's effectively an industry standard. It doesn't have any formal stamp of approval from a regulatory body like these, but nevertheless the industry together agrees to adopt it. So the most important one of those is one that we won't meet until somewhat later, because it's only just developed a new standard in video coding called AV1. It was only finalised last year, and some of these industry forums because they don't have the weight of the approval of these international processes, they are not always highly successful. But this particular industry forum, which whose name escapes me at the moment, Alliance for Open Media, thank you, comprises all the really big guys in video, so Apple, Google, Adobe, Microsoft, Netflix, right? And so once you get all these guys together and they agree on a standard, then it's probably significant. Okay. And the reason, actually, I know I'm anticipating a lot where we're going, but the reason that they got together and developed their own standard was that they didn't like the fact that some of these standards involve patents and potential royalty payments and so on. So they just want to facilitate the delivery and sale of their media, provide services over the internet, and they don't want to be burdened with having to worry about licensing fees. So anyway, that's, as I say, getting somewhat down the track. in terms of the formal international standards, the timeline, or timetable of the most significant ones is shown here. The H series recommendations are those that come from the ITUT. It's just their numbering system. And the MPEG ones are maybe obvious. So what we're saying is that the first significant video coding standard emerged around 1990 with this H.261 version out of ITUT. Around that time, the ISO group started up and developed MPEG-1 and then MPEG-2. We'll understand the differences between those in a little while. And the two groups really collaborated in the development of these later versions. And the most recent standards come out a few years ago, but they keep on providing extra parts and extra refinement, and that's this high efficiency video coding standard. So I might refer back to that every now and again just to provide a bit of perspective as we go through some of this material. But since we're talking about standards, just as an aside, it's 7:30 now. I'm assuming we're going to do the usual thing we've done the last 2 weeks and just push on, having had one break. We'll just finish a bit early, finish by before 8. Is that all right? Okay. Let's consider for a moment what a standard has to do. So a standard is not there to completely define everything that's in an encoder and everything that's in a decoder, but rather it should specify the minimum, in fact, to allow encoder from manufacturer A to talk to decoder of manufacturer B. Okay. So what's actually standardized is that interface, right? So that if that's completely specified, then I can build a decoder, and my decoder will understand the protocol that I see here, and will understand all the bit patterns. We'll understand the Huffman codes, for instance, and we standardize the decompression engine. So how you handle the signals that you receive here. Now, by default, that's saying a lot about the encoder, but what you're really saying is how to interpret this data here. Does that make sense? So if this decompression engine says, take this data that you receive from this interface and do an inverse DCT, then of course, back here you have to provide a forward DCT. But there are some things in here that you do not have to standardize. And one of them we just talked about, actually. I wonder if anyone can guess what it might be. That's an encoding process that you will not need to standardize.
Maybe the decoder inside.
Pardon?
Maybe the decoder part for the prediction or something.
Well, remember we always have to have the same prediction at the encoder as the decoder, so that has to be the same. We just talked about motion estimation and motion compensation. So if this guy has to use motion vectors, then the protocol for transferring those motion vectors must be transmitted over this interface, so we need to standardize that. But what other part of the process do we not have to standardize?
Motion prediction.
Motion prediction, exactly, the motion estimation. So whether we use exhaustive search or the logarithmic approach or some other new algorithm using some hexagonal search pattern, doesn't matter. As long as we understand what these motion vectors are that are coming across this interface, that's what needs to be standardized. So no standard will say, this is how you do motion estimation. Yeah. There's also, we will talk about this in a few weeks' time, but something else that will need to be standardized, it's a kind of minor part of the whole system, but in sending data over this interface, we need to be sure that this buffer is not going to overflow. Okay, So you need to have some parameters that define that. But there's flexibility in this system to allow individual manufacturers to differentiate their own products. So if someone thinks they can build a decoder that recovers better in the event of errors or lost packets or something like that, then that's fine, that's outside the standard. Or if someone wants to build a fancy adaptive filter here to try to remove the appearance of those blocks, then that's outside the standard. It doesn't impact on the ability of one encoder to talk to a decoder. And at this end, maybe we want to, in fact we'll talk about this later, maybe we want to filter that signal that comes from the camera to remove, to smooth it out a bit, to remove the noise. Because if you can imagine what noise is going to look like in a video signal, our DCT assumes that our image is smoothly changing. So the presence of noise means, what does it mean in terms of frequency components? What do you think? Going to be low frequency components or high frequency components? High, or actually a range, but noise will have, in theory, white noise has all frequency components, but noise will introduce some randomness in the pixel values, and so to accurately represent those changes, we would have to have a lot more high frequency components present. And if we waste our bits defining the high frequencies that would allow us to reconstruct a signal that's just noise, that's a bit of a waste of bits. So if we filter them out initially, if we can do so without smearing the whole picture, then we save bits and the whole process is more efficient. But we don't, the decoder has nothing to do with this. So again, it's something that we don't need to standardize. So I think I've made that point. Let's move on. A look at this H.261 coding standard. So I won't worry too much about its application because it's old, it's not used anymore. Maybe you can apply it with some software video coding systems, but it's essentially been superseded. It was originally intended for video telephony and video conferencing type applications over ISDN networks. ISDN networks you probably haven't heard of because some of them still exist, but they're being replaced by IP networks. They were the first digitization of the telephone network, essentially. ISDN stands for Integrated Services Digital Networks. So the idea was, the telecommunications companies had this vision that they would eventually digitize and then broadband their networks to carry all telecommunication services, but then the computer community, this is the 30-second summary of the emergence of the internet, but the computer community came up with IP and Ethernet and their own methods of carrying broadband services, and that essentially dominated. So these ISDN networks went out of favour, although, as I say, there probably are still some hanging around, provided by telecommunications providers to specific companies for various purposes. But in terms of the codec, it just meant that it had to operate at a multiple of 64 kilobits per second. And because it was intended for video telephony and video conferencing, one of its objectives was to try to unify communications between the different video standards, which is no small feat. But remember that the US and Japan and some other countries have 30 Hertz based television standards, which means that their cameras for video telephony would be 30 Hertz and their monitors would be 30 Hertz. Europe, of course, was based on 50 Hertz. So to be able to take a signal from one and have it appear at reasonable quality in the other was one of the objectives, to allow international video conferencing. One of the reasons I wanted to include this encoder was just this picture, because this is a block diagram that's actually taken from the standard, and it's already hopefully pretty familiar to you, even though we haven't talked about some of these blocks. we see this familiar prediction loop here. Okay. A couple of extra things to talk about. There's this loop filter, which just allows for some smoothing in this prediction loop, and I'll explain why we might want to do that in just a moment. We haven't talked about this adaptivity, but actually, can anyone see what that's going to do? That switch is going to do? What happens when it's flipped into the upward position?
It will see the predictive, besides the predictive image, I think. When the switch goes up, then see the predictive that from P block.
Ah, but that's, no, this is going to the P block, so this is actually the prediction state. But if that switch was flipped up there, then it wouldn't be looking at the error, the difference between these guys, would it? It would be taking that signal directly in. So that's to allow for the allow you to switch between encoding the image by itself or encoding the prediction, just depending on which is better. Okay, so if there was a sudden change in for some blocks in the picture, we can't predict them from predict it from a previous frame, so we just code it fresh. Yeah. We'll come back to that point anyway. The other block that we haven't talked about is the coding control, but of course it was kind of assumed there because we need some intelligence in the encoder to make decisions about when we use the prediction, when we encode the prediction signal or when we encode the original signal, what quantizer we use for particular blocks, whether we use this loop filter, we'll come back to that. So there is some coding control intelligence there that we haven't seen in the earlier block diagram, sorry. But otherwise, it has the components that are familiar to us. T is transform, like the DCT, Q, and Q to the -1, and this prediction loop is familiar to us. And I'll talk about the outputs in just a moment. But I just wanted to expand on this loop filter, the principle behind this loop filter. The idea is to remove artifacts that are used in prediction. So if this is our new frame that we are encoding, and we're encoding at a fairly low rate, then our prediction signal, the one that's been reconstructed from encoded data, might be fairly blocky. Right? It might look like this, with all these sharp block edges here. And so maybe that's not the best, not going to give us such a good set of data to predict this new frame with. It might be better to just blur it out, to smooth it out, and use a blurred version to predict this signal. So that's the idea of allowing for that this loop filter thing. Does that make sense? Right, those sharp edges that are present here in between these blocks were not present in the original signal, and it's not necessarily going to match very well with anywhere nearby in this new frame. So even though the blurred version is also not going to be a perfect match, maybe it'll at least allow matching with the main features. So that's the idea. And then the coding control is the one that makes the decision about whether to include it. Here I've just listed what the outputs are. No surprises, I don't think, but let's just go through them quickly. So the P is just a flag to tell us whether we are encoding interframe, so differences between frames, or intra-frame, just within the frame. Is that terminology okay? Yep. So intra-frame is just like JPEG. Right? It's not doing anything in the temporal direction. The interframe is doing the prediction error. T is a flag for transmitted or not, so that's like the conditional replenishment. Is this block even coded, or has it not changed enough to warrant it? QZ is telling us what the quantizer step size is that's used in encoding this data. Q is the actual quantized values. V, the motion vectors, we said had to be sent to the decoder, and now that we've got this loop filter thing here, we need to indicate to the decoder whether it's used in each block. So we can relate all of those outputs back to what we talked about earlier, I think. Look, I included this slide, but I don't want to attach too great a significance to it because it is a little bit dated. I'll just reveal all the graphics. But at the time that this early standard was developed, there were fixed television resolutions, fixed image formats that were available to it, and fixed image formats that it could generate, because the only cameras that were available were television cameras, the only monitors were television monitors. So these days we just scale and transform and display on a PC, but you couldn't back in 1990 or thereabouts. And that's why it was a challenge for this particular standard to achieve this interworking between different television formats. But it was achieved by defining this thing called a common intermediate format, which actually comes out as being the result of a committee and a compromise, because the definition of this common intermediate format was that the one set of parameters, the spatial resolution, was defined from the 50 Hertz world, and then another parameter, the picture rate, was defined from the 60 Hertz world. So this common intermediate format involved a set of parameters to define the video format that was actually encoded, and then it was the responsibility of the receiving end to convert it back to match the particular display device. And there was this CIF, common intermediate format, and then a quarter CIF, because we were operating at very low rates, very low qualities. At the lower rates, it was better to reduce the resolution from a standard TV picture up there by a factor of 2 in each dimension to get the CIF one, and then by another factor of 2 to get the QCIF one. But as I said, I don't want to spend too much time on it because it's not something that we've had to carry through to other coders. You might occasionally come across the acronym CIF, and that's where it comes from. Just halving the conventional, the standard resolution figures from the 50 Hertz world to obtain the resolution, and maintaining the frame rate from the 60 Hertz world for the frame rate, to allow for this interworking. Yeah.
Where's the 29.97?
Oh, okay. Yeah. It's a hangover from the analog days. The nominal frame rate in the US was 30 Hertz, but if I remember this correctly, because it's stuff that's kind of history now. When they introduced colour, there was an additional carrier signal put into the analog television signal, and because of the I'm not familiar with the precise details, but because of possible interference issues between this colour subcarrier and the audio carrier, they needed to shift timing a little bit, and so it turned out that by changing it by a factor of 1/1000th, they solved this problem. So that's why 30 Hertz became 29.97. So it's kind of historically interesting, but it's gone into the past now because we're all digital these days. Okay. So, well, for these H.261 coders, to make sure that they could talk to one another,
this lower resolution version was compulsory, and optionally they could signal one another and say, we actually have this, we can support this higher resolution as well. Just a word about the use of this particular frame rate, 29.97, and how you might think, well, how does that provide into working? Well, it provides into working because the pictures can be skipped. So although we have this nominal, I'm going to refer to it as 30 hertz, close enough. Because we have this nominal 30 hertz frame rate between encoder and decoder, we can just nominate any frame to be associated with any of those time ticks, if you like. So if we had a 25 frames per second source, we would just say, well, that frame goes to that, is labelled with that time, this frame is labelled with that time, this frame is labelled with that time, and so on, but we're eventually going to get out of sync, so we just skip one. We just don't encode this one, and then we go back and do this. And the decoder will just you know, the decoder is just, if the decoder is displaying 30 hertz, it will just show these frames a little bit bunched together, and it will freeze one there and then go on to the next bunch. So in a low quality video conference, you're probably not going to notice. But the important point here, even though it's really pretty historical anyway, but the point is that we don't have to do any sophisticated filtering and resampling to try to get from 25 hertz to 30 hertz for this compatibility issue. We just use this alignment of time slots to get around the problem. And of course, if we wanted to reduce the frame rate even more, we would just do something similar. Just say skip certain frames. Okay. And it's worth remembering that H.261 was expected to be implemented in hardware, and so that's why all these resolutions and frame rates were all fixed, hardwired, and today they can all be done flexibly in software. One of the structures that was introduced in H.261 and was carried forward in some of the other standards was the idea of a macro block. And so a macro block is simply the element on which motion estimation and compensation is carried out. So in the case of H.261, it was a fixed block size of 16 by 16 luminance pixels, and because the chrominance was subsampled by a factor of 2 in both directions, we talked about that. So this is there's a challenge for you. Who can remember the code, the numerical set of 3 numbers that define the subsampling in both dimensions? You know what I mean? So 4 something something. 420. Well done. Yes, exactly. That's right. So 420 was built in. 420 subsampling was built into H.261, and that meant that we had half as many chrominance samples as luminance. No, we had a quarter as many, but one set for CR, one set for CB. And so the idea was to define this macro block structure, which gave us 16 by 16 luminance pixels and 8 by 8 chrominance. So the 8 by 8 sets were well suited to the DCT, and the motion compensation matching was based on the 16 by 16. Okay. So, I mean, there's no technical requirement why it has to be of this format. It was just designed in as a convenient set of numbers. Sorry. Okay. So in H.261, the 420 chrominance sampling meant that we needed half as many chrominance samples in the vertical direction and half as many in the horizontal. Where those samples were assumed to lie is a design decision, right?
So we could have said, we could have shifted all of these yellow dots. The yellow dots are intended to indicate where the chrominance samples lie. They could have been shifted up and to the left so they always align with one of these luminance ones, but in fact they were interpolated in a way that assumed that they were at the midpoint, and that just meant that it was easier to generate some of these others. When we need to reconstruct the full resolution colour to actually send it to a monitor, then we can, each of these sample points is closer to an output sample location. Does that make sense? Yeah? Sorry. So we need to create these colour samples at these interstitial points that didn't exist in the original. Originally, we had from the camera we had RGB at full resolution. There's no sample value at those interstitial locations, and so we need to do this sort of process. So for each block of 4 original pixels, we have RGB values for each. We convert RGB to YCRCB. Then we do our 420 subsampling, which means that we can create our chrominance signals just by averaging the 4 values nearby. How are we going for time? Okay, we'll finish shortly, but yeah, let me just do this this last step, which is looking at the hierarchy of how the picture components were put together. And I'm certainly not going to do this for each coder we look at, but I'm going to look at it for this simple one, because it just gives you a feel for, or at least an understanding of the logic of how you can define the different picture components. So that'll make sense in a moment, I hope. So a hierarchy was defined whereby we said we're about to, there are bits in the protocol that says we're about to define a new picture, and the picture is split up into what are called groups of blocks, which is actually a set of macro blocks. So within each group of blocks we define a set of macro blocks. The macro blocks are in turn split up into the luminance blocks of 8x8 and the 2 chrominance blocks of 8x8, and they're the ones that actually go to the that actually go to the DCT. Okay, so this is not really important. Again, it's a consequence of the fixed resolutions that we used. These groups of blocks, when put together, had this sort of arrangement for the 2 resolutions, but I'm not too concerned about it. Just to give you a feel for the relative scale, if this was the full resolution, the CIF image, then groups of blocks would be this big. So there were 2, 4, 6, 12 of them in the making up the picture. 33 macro blocks in each of those groups of blocks. And each macro block was divided into the 8x8. So in defining the picture and the blocks that make up the picture, there was a hierarchical protocol that was defined. So, and I'd like to, just before we finish up, I'd like to just go through a couple of slides to illustrate this, and then we'll finish up. And so again, the reason I want to go through this is not because it's so relevant for today's coders. I just wanted to use this simple coder as an example to see how we can logically define the information we need to reconstruct a video, an encoded video. So the picture layer protocol. The first, there's a reserved start code that allows us to synchronize. So if we're just starting up the connection or we've lost sync somehow because of an error, we can just look for one of these picture start codes. And as soon as we receive one of those, we think, aha, okay, we're about to encode a new, I'm about to receive data defining a new picture, so I need to expect to fill in blocks starting up in the top left-hand corner. There's a temporal reference which tells us what our frame number is so that we can put it into that 29.97 Hertz structure. Some information about the picture type. So is it QSIF or SIF? Which resolution is it? And there are various modes that are used for video conferencing. Have I, for instance, split the screen up so I can get more people side by side, this sort of thing. But after we've done that, this information that applies to the whole picture, then we go into the group of blocks layer. So we're going to define each group of blocks, and we're going to go round and round here as we work our way through each of the 12, maybe 12 groups of blocks. So inside the group of blocks, we've got another start code for synchronization. We've got a group number, so we know which group of blocks we're talking about to ensure that we're putting the data in the right place in the picture. We've got some quantizer information here. This provides some quantizer, so it tells us which quantizer we will be using within this macro block layer, but I'll come back to that point if I have time. And so having defined essentially where the group of blocks is, we then jump inside and we define each macro block. So we go round and round that macro block layer until we finish with this group of blocks, and then we go back and there's a new start code for the next one. Within the macro block layer, this looks a little bit more complicated, but it's straightforward if we follow the arrows and think about what it means. First of all, we could bypass everything because we're not encoding this particular macro block. We can go to the next one. If we're encoding it, there's a macro block address to tell us which in the 33 possible locations it exists. And we want to know the macro block type. So is it intercoded or intracoded? Is the motion compensation used? Is the loop filter on and off? If we're encoding it, then we have the opportunity here. I mentioned the quantizer is defined a layer above, but here we have the chance to override what was included before. So if we want to change the quantizer information from the layer above for this particular macro block, then we can do it. Think for a moment about why you might want to do that, or why you have that capability. Motion vector data, so the horizontal and vertical components of the motion vector. Having defined having got to the stage where we're about to encode the block, this tells us which blocks have at least one coefficient, so which blocks are actually encoded of that set of 6. And then we get down, to the actual blocks themselves, the 8x8 blocks, and they simply we simply send the transform coefficients until we get to the last non-zero component, and then we say end of block. So this is the zigzag thing again. Okay, that's been a little bit fast, but I hope it made some sort of sense. There are some ways of representing the transform coefficients a little bit more efficiently, just from observing common patterns, such as it's common that we have a certain number of zeros followed by some level. So those combinations are assigned variable length codes using Huffman code type techniques. Okay, end of block. I've got got 2 more slides. I know I said I'd finish as early as I could, but if I could just finish H.261, I think it would be useful. How do we encode macro block addresses? Some of those macro blocks might not be encoded. So while the obvious thing to do might be to just send the number that defines each macro block, so we would have 1, 2, 3, skip 4 and 5, and 6, 7, 8, and so on. In fact, they're encoded in a relative sense, so differentially, if you like. So we indicate the address of the first macro block in this set, number 1, in this case, we're encoding it, and then we just send the number that we need to jump. So we just need to jump 1 to the next macro block, we need to jump 1, then we jump 3, and so on. And we do that for, I think, reasons that are probably obvious, right? We end up with a series of small numbers which are easier to code, fewer bits than if we were encoding these absolute addresses. Let's change the... Oh, right, so we're encoding differentially here. Why might that be a good idea? We just talked about that, and I included this table just to show you that things like Huffman coding really is used in practice. So built into the definition of the standard is a set of variable length codes defining these macro block addresses, and I chose that as just an example. There's the other stuff we need to encode, but I'm not going to go into all that detail. And you understand about the relative addressing, and so the most common macro block address that number that we're likely to receive would be 1, right? We just encode the next one. So this is the most common one, so it's given the shortest code word. So I just wanted to relate that back to what we talked about with regard to variable length codes and Huffman coding. So one last point, I think I've said that before, but one last point before I do let you go, which is just to resolve this, not that. Sorry. To resolve this question of why do you think would be a good idea to provide this quantization information here, but then allow for it to be overwritten here? It's maybe not so obvious, but as soon as I tell you, it's like, oh. Okay, well, we've gone late enough. So the idea is just that if this quantization step size is good enough, then it just saves having to define it for each macro block inside. So it just saves bits. But if it's not accurate enough, or we have enough bits available anyway, then we can redefine it inside, and that's the only idea behind that.
So it will be more loosey, that code.
Would be more what? Sorry?
Lossy.
Well, could be. Yeah, I suppose if we just had the one fixed quantizer, it's not going to do as good a job as if you change it for every macro block, but we save bits. We can use them elsewhere. Okay, I've kept you later than I intended, so I apologise, but that'll do for tonight, and we'll continue next week. I think I'll give some thought to those individual projects with what I've already put on the LMS, and maybe we'll talk about the expectations and what we need to do next week as well. Okay.
One question. Two pictures with elephants, with the CRF and QCRF.
Yep.
So why do we bother to do this? I didn't follow you at the page, the two elephants page here.
Yeah. Where are we? Yeah. Okay.
And then
Yep.
previous one. I know a previous one was CI and QCI.
Oh, this one. Yeah, I went over it very quickly.
Yeah, so what's the purpose of this slide? I mean,
Well, it's just showing how we obtain these fixed resolutions that were used in the standard. So this is a standard television signal, right? Which in the digital world was 720 by 576. And so by halving that resolution for the luminance, that gave us these figures here that defined this CIF resolution. Okay. So if you came from the 60 hertz world with 720 by 484, you'd have to scale, or you'd have to create a picture with some black around it or something like that to make it look like 352 by 288.
ah, yeah.
Yeah? But the frame rate was defined as coming from the 30 hertz world, right? So it's almost 30 hertz. Okay, so that when that was used as I described in the other slide, where you could skip pictures if you wanted to. Does that make a bit more sense?
Yeah, it's just the transition between two standards, two
The
types of video.
It's,
So this is a type of video, and how can we transform?
Okay. So, well, if we always in the 50 hertz world, it's easy, right? We just subsample by a factor of 2 in each dimension, so we get that resolution, and then we upsample at the receiving end. Okay, and the pictures will be conveyed in this way, but we'll be able to extract them and put them in the right time. In the right time slot at the far end. What's more interesting is if we're in those different worlds. So if we start from the 60 hertz world, we've got 720 by 484. If we subsample that by a factor of 2, we end up with
360 and 240.
I shouldn't have used those numbers. Anyway, we end up with only 242 lines. So we probably just make 22 lines of black at the top, 22, right? We create a new array, and that means it can be received and decoded and displayed on a 50 hertz display. It just means it will have some black top and bottom. And the frame rate is handled as I said before. So with this arrangement, we could transmit at 29.97 hertz, and at the receiver in the 50 hertz world, we would just pick off whatever frame was closest.
Okay.
Okay.
And the macro block.
Yep.
Yeah. What's the purpose of macro block? It's just the motion.
It's the unit that we use for motion estimation.
So is it uniformly distributed?
How do you mean?
It's because
so
one picture are all macro blocks uniformly distributed? Like on the first line there are 4, and second line there are 4, or we define the location of every macro block?
Well, the macro blocks in this standard, the macro blocks are grouped up so that there are 33 macro blocks in each of these group of blocks.
Yeah.
Yeah.
So, but in the previous example, like the football player, you could just choose some block. Is that a macro block?
Yes. Well, I didn't mention it here because we hadn't talked about the standard or macro block. But yes, each one of those is a macro block.
Okay.
Yeah. But in that standard, they decided on a fixed size for that macro block, 16 by 16.
Okay.
Yeah.
Yeah.
Great. No worries. Did you have another question? Sorry?
Once about these lectures, how to know how big we need to.
Well, it's a design decision. I mean, it's a compromise considering how much processing you want to devote to this task.
For example, from the big to small, we find the big one and then make it smaller and smaller. Is it or
no? This is the
it was designed before.
No, this is before that. This is independent of how we do the searching. This is saying over what area will we search. Right? If we're about to encode this block, should we search for it anywhere in this huge area, or do we only want to look nearby?
Not mean it.
Ah.
But I mean the not the searching area is
Yeah. The size of the
the
box.
size of
Okay.
the box,
Yep.
because we don't know how big the objective,
No,
the
that's
moving
right.
objective.
We don't. That's right.
So,
So it's something of a compromise, and we just build it into our design. And there are those trade-offs that I talked about. If we have a larger block, we'll have fewer motion vectors to send, but we will get a less accurate prediction. So